Hey everybody, it is January 25th, 2009. I'm Sonic Suns. I believe this is my 394th video, but who's counting? No. You may have heard of something called the Game of Life. It's this board game that you get and you go around a little track, and that doesn't matter. It's a random little board game that I'm talking about. There's a entirely different thing called Conway's Game of Life, which isn't even hardly a game in the normal sense of there being players and an objective and trying to win. It's more of an idea of a pattern, which, though that sounds rather bland and dumb, eventually means a whole lot more to intellectual pursuits than, you know, the little car moving around the little track. It's practically zero strategy. Though I guess this, in its one way, has even less strategy, but so much more mystery. Here's the deal. You take a big old rectangular grid, made of little squares, and we call these squares living or dead. They're typically colored that way, either black or white. And this grid can be as big as we want, doesn't really matter. You color in some of those squares, cells, they're often called. Color those cells, okay, some of these are, black, and most of these are white, or do whatever you want. And then there are certain rules as to what happens to each of these cells each step of the program. Sometimes these steps are called ticks. They're like, okay, so we figure out what will happen to this guy, and this guy, and this guy, and this guy. We figure out everything at once, and then everything goes tick and changes all at the same time. So there are a couple of very simple rules of this, right? So number one, if any cell is fewer than 2 live neighbors, it dies. It goes to the white or dead state. And neighbor, by the way, is 4 directions and the 4 diagonals. It has to be immediately adjacent, though. If you have fewer than 2 live neighbors, you die. If you have more than 3 live neighbors, you die. If you have 2 or 3 neighbors, then you just stay exactly as you are. You remain alive. And if there's any empty cell that's got, or any empty section, that's got exactly 3 live neighbors, then that one becomes alive, as if, like, the others would reproduce. The other things we think of as underpopulation, overcrowding, sort of stability with that third rule. Anyway, so those are the rules. Those are the only rules to the whole thing, right? And the deal is you set up some sort of pattern, and then you let it run and find out what happens. And it turns out all sorts of craziness can happen. You start off with, like, most of the random things you come up with are just going to die out in a couple generations. But if you have, for instance, a thing that's 3 in a row, that'll live. That'll be like this way, and then this way, and then this way, and then this way, and this way, this way, keep going back and forth. If you have 4 in a little box, that'll stay that way forever. If you have a couple of other funky things, you can see there's, I'll put up a link to Wikipedia. It's got little animations and stuff. Something called a glider, which will recreate itself in various ways and move as it goes. So it'll go down the path basically to infinity. And then there's all sorts of different ways to do that. They eventually figured out how to do what's called a Gosper glider gun, which is this pattern where the things bounce back and forth, and every time it bounces, it makes another glider that shoots off. And from that, you can prove that the thing, given infinite steps, will just keep on growing on and on to infinity. You think, well, that's interesting, but who cares? Well, there's a thing called Turing. You've heard of it, the Turing test, universal Turing machine, Turing completeness and stuff. It's basically the ultimate basic rules on what you need for a computer. It is a universal Turing machine. It's a hypothetical machine that was proposed that you could build if you wanted to. It doesn't take any fancy physics or whatnot. Just a basic idea of a machine. And given just a couple of simple requirements on this machine, a couple of simple rules that you should build it according to, it can do any computation ever. Any computer you could absolutely imagine, anything it might possibly calculate, could be calculated on this simple thing that doesn't even involve a microchip. And you may be wondering, well, why don't they build these things? Well, because it would take a ridiculous amount of time, like to do that calculation, you see. Building the machine would be easy, but the computers, of course, do this much faster. The thing is, though, we can prove that given enough time, this machine can do anything. And any calculation, that is. Anything at all. You can turn whatever result of any absurdly complicated problem you want to give it. Right? Turns out Conway's Game of Life has that same property. theoretically, you could program in using, you know, okay, just at the beginning, which cells are alive and which cells are dead. You could, in a sort of weird coded fashion, program in anything at all, and by the results of this, you could take blah, 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 and okay, so after 60 steps, you know, this thing was over here, and that thing was over there, yada, yada, and that will be the answer to your question. Whatever your question was. It'll calculate anything. And I got to thinking about how life began. And theoretically how it works is there's a Big Bang, and then all sorts of crap, you know, explodes, basically. I mean, that's the best word we have for it. And then there's just, you know, bajillions of little random particles randomly floating around with basically no rhyme or reason, except for the general, we're all exploding. Beyond that, no, we're just everywhere. But everything starts to organize randomly. You happen to come across, you know, galaxies, stars, planets, things like that. Within even just our one planet, once that finally organized, there's a bunch of random crap lying around. Random bits of, you know, various elements. Random atoms. With their random subatomic particles. And randomly, some of them happen to form a self-sustaining thing. You know. That's how the planet started up in the first place. Is a bunch of stuff happened to clump together, and it turns out clumping together is, you know, a way of enduring. Not that they were trying to endure, not that the particles were like, oh crap, we need to stay alive, or whatever. No, they're not even alive. But, because this pattern is an enduring pattern, at least from the human perspective, the Earth has been around for all this time. There's certain, on the small scale, little things like this little piece of this and that together will make a very, very basic life form that'll sort of sustain itself. Those, in turn, complicate into slightly more complicated life forms. And eventually, with all sorts of randomness going around, all sorts of things and stuff living and dying out, and evolution and whatnot, we eventually come to all the creatures we've ever heard of, and humans, and our intelligence, and all that. That's pretty cool. So here's the thing, I was just thinking. Suppose you played a really massive game of Conway's Game of Life on, I don't know, put it in a supercomputer or something. Start off with a really big grid, and keep expanding this grid as we go. Like, with every step, just, you know, double the grid or something, I don't know. So there's no real limit to it. At any given point, you'd want to limit because your computer can only do so many calculations, but just keep making it bigger as we go, and computers keep getting faster anyway, right? Now, have the computer, on every step, randomly select some percentage of cells, and randomly flip them from on to off, or from living to dead, or from dead to living. This is also called on and off, black and white, those sorts of things. Pick a random, you know, this one, this one, this one, this one, this one. Flip them all, and then apply all the rules that you normally apply. And every single step, you do a little bit of randomness. Now, at some point, randomly, we'll start to form a couple of structures that happen to work, right? At some point, we'll have that three things in a row, randomly. That'll be interesting. And then, randomly, something will make like a glider thing, and something will make maybe something more complex thing, and it'll tend towards structures that can deal with randomness, right? If you have just, you know, any structure that's very simple, you know, take that three thing, you take out the middle, and then boom, that's gone. But if something bigger and more complex might be, look, you can, you know, change around 10% of us, but 60% of the time we can survive that, and it'll still reform, if not exactly itself, in something relatively similar.